This is a multiple-choice question, focusing on testing your knowledge of the sklearn. Utils. Sparse funcs underscore fast libraries in place underscore csr underscore row underscore normalize underscore l1 function. It's designed to assess how well you understand its functionality and the benefits it offers when working with sparse matrices. This line poses the core question. We need to evaluate the truthfulness of several statements related to the behavior and performance of the in place underscore csr underscore row underscore normalize underscore l1 function, which is part of scikit-learn's utility functions for handling sparse matrices. Let's examine each statement carefully. Statement A claims that the function normalizes each row of the input sparse matrix, X, so that the sum of the absolute values of its elements equals 1. Furthermore, it modifies the matrix directly, in place, without creating a copy. This aligns with the typical meaning of L1 normalization. We'll need to verify this against the function's documentation. Statement B asserts that the function correctly handles rows containing only zeros. It implies the function won't crash or produce unexpected results when encountering such rows. We need to consult the documentation or test cases to confirm this behavior, as it's not inherently guaranteed. Statement C suggests the input matrix must be square. Same number of rows and columns. This is incorrect. Row normalization operates on each row independently. The number of columns doesn't affect this process. The shape of the matrix is irrelevant to row normalization. This statement posits that using in place underscore csr underscore row underscore normalize underscore l1 is much faster than creating your own row-wise L1 normalization using standard NumPy and SciPy tools, particularly when dealing with large sparse matrices. This is often true because the scikit-learn function uses optimized algorithms designed specifically for sparse matrices, those with many zero values, avoiding computations on unnecessary zero elements. This section describes what the function takes as input and what it produces as output. Think of it like a recipe. It lists the ingredients, input, and the finished dish, output. The function starts with a special kind of matrix called a compressed sparse row, CSR, matrix. This is a clever way to store matrices with lots of zeros, making calculations much faster. X represents this input matrix. This is the main part of the function, where the action happens. It's going to do some number crunching, and that's where the magic begins. The function performs L1 normalization. This means it scales each row of the matrix so that the sum of the absolute values of its elements equals 1. Importantly, it does this in place, meaning it directly modifies the original matrix X without creating a copy. That saves memory and makes it more efficient. After the processing, the function returns the modified matrix X. Each row is now scaled to have an L1 norm of 1. This is a crucial point. This function is specially designed to work efficiently with sparse matrices, like our CSR matrix. It avoids unnecessary calculations on the many zero elements, making it much faster than general-purpose matrix operations. This statement introduces the function in place underscore csr underscore row underscore normalize underscore l1 from the scikit-learn library. It's a function that works with sparse matrices, a special type of matrix with many zeros. The in place part means it modifies the original matrix directly, without creating a copy. CSR stands for compressed sparse row, an efficient way to store sparse matrices. The L1 refers to the L1 norm, which is the sum of the absolute values of the elements in a row. The function normalizes each row such that the L1 norm becomes 1. It's all about efficient math for sparse data. This is the core question of the quiz. It asks us to determine which statements are accurate regarding the behavior and efficiency of the in place underscore csr underscore row underscore normalize underscore l1 function. Let's explore each statement carefully. Statement A claims the function normalizes each row of a sparse matrix, represented as X, so that the sum of the absolute values of elements in each row equals 1. Furthermore, it states this happens directly within the original matrix, in place, meaning no new matrix is created. Is this true? Statement B suggests that the function manages rows containing only zeros without causing errors. This needs further investigation, as it depends on the function's specific implementation and the version of the library being used. Does it handle these cases smoothly or does it throw an error? Statement C states that the matrix X must be square, same number of rows and columns, for the function to work correctly. This is about the shape of the matrix. Row-wise normalization does not require a square matrix. This statement is clearly false. Statement D proposes that the specialized scikit-learn function is considerably faster than a simple row-wise L1 normalization done using standard NumPy and SciPy functions, especially when dealing with large sparse matrices. This is a performance-related statement. Is this optimized function really faster? This refers to a specific function within the scikit-learn library in Python. It's a tool designed to efficiently normalize rows in a sparse matrix. A sparse matrix is a type of matrix where most elements are zero, allowing for memory-efficient storage and computation. The "in place" part means it modifies the matrix directly, without creating a copy, which saves resources. The "CSR" refers to the compressed sparse row format, a particular way of storing sparse matrices. Finally, "L1" denotes L1 normalization, which means each row is scaled so the sum of the absolute values of its elements equals 1. This is the core question of the quiz. We're being asked to evaluate the truth of several statements about how this function works. The function's name gives some clues, but to be certain, we need to examine the function's documentation or recall its behavior from previous experience. Statement A states that the function normalizes each row, making the sum of absolute values equal to 1. And does it directly on the input matrix "X" without creating a new copy. This statement matches the core purpose of the "in place _CSR row _normalize L1" function. Statement B claims that the function appropriately handles rows containing only zeros. This requires checking the function's behavior in the official documentation. Zero rows present a special case that needs to be explicitly managed to avoid potential errors. This statement asserts that the input matrix "X" must have an equal number of rows and columns, B square. Row normalization is independent of the number of columns, therefore, this statement is false. Statement D claims a performance advantage. This is likely true because specialized functions for sparse matrices are usually optimized for speed, avoiding computations on the many zero entries. NumPy and SciPy are general-purpose libraries, so their methods may not be as efficient for large sparse matrices. A sparse matrix is a matrix where most of the elements are zero. The CSR, compressed sparse row, format is an efficient way to store and work with such matrices, saving memory and computation time compared to storing all the zero values. L1 normalization is a technique where each row, or column, of a matrix is scaled such that the sum of the absolute values of its elements equals 1. This is often used in machine learning to standardize data or features. An in-place operation modifies the original data structure directly, rather than creating a new copy. This is generally more memory efficient. Optimized algorithms are specifically designed to take advantage of the structure of the data to perform computations faster and more efficiently. In the context of sparse matrices, optimized algorithms avoid unnecessary calculations on the many zero values. This refers to a specific function within the scikit-learn library in Python. It's a powerful tool for normalizing rows of sparse matrices. The function's name tells us a lot. In place means it modifies the original data directly. CSR indicates it works with compressed sparse row matrices, a format efficient for sparse data. And row _normalize L1 implies that each row will be normalized using the L1 norm, sum of absolute values. Let's explore what that means in more detail. This statement discusses how the function behaves with rows containing only zeros. A zero row has an L1 norm of 0. The question is whether the function manages this situation without causing problems like errors or undefined results. To know for sure, you would check the scikit-learn documentation. This statement is about the shape of the input matrix. A square matrix has the same number of rows and columns. However, row normalization only concerns the values within each row. The number of columns is irrelevant. Hence, this is false. This compares the speed of the scikit-learn function to a more basic method using general-purpose libraries like NumPy and SciPy. Specialized functions like and place CSR row normalize L1 are optimized for sparse matrices. Because many elements are zeros, these specialized functions cleverly skip unnecessary calculations for huge speed improvements. This is a multiple-choice question about the S function. We'll explore the properties of this function. Ready? The question asks us to identify which statements correctly describe the behavior of the function. This function is part of scikit-learn, a popular Python library for machine learning. It's used for working with sparse matrices, which are matrices that have many zero values. Statement A says the function normalizes each row. L1 normalization means scaling each row so the sum of the absolute values of its elements equals 1. In place means it changes the original matrix directly, without creating a copy. Let's see if this matches the function's behavior. Does it sound plausible? Statement B says the function handles rows containing only zeros without causing an error. Many functions might fail or produce unexpected results when faced with all zero rows. What do you think? Is it likely to behave in a way that avoids errors for this specific scenario? Statement C claims the input matrix must be square. Same number of rows and columns, row normalization only affects the rows. The number of columns is irrelevant. Does that make sense? Could a non-square matrix be processed successfully? Statement D suggests this function is optimized for speed. It compares its performance with a basic NumPy, SciPy approach for handling large sparse matrices. Matrices with lots of zeros. Functions built specifically for sparse matrices usually outperform general-purpose functions. What's your intuition on this?